Looking at electromagnetic induction then, electromagnetic induction is how we make electricity, and it comes about where the field, magnetic field through a conductor is changing, either because we are moving the conductor through the field and so it is cutting through field lines, or because the field around that conductor is changing. And we'll look at that with the transformer. So if we change the direction of motion of our conductor, we move the conductor down through the field, we get an induced current in one direction. If we move it up, we get an induced current in the other direction. But you can see that if we move it along the field lines, remembering the field lines run from north to south, if we move it along the field lines so that it isn't actually cutting through the field lines, then there is no induced current. So it is only where the field through the wire is changing, through the conductor is changing, or another way of looking at that is it is only when the wire or the conductor is cutting field lines that there is an induced PD across the conductor, and in this case, because we have a complete circuit, an induced current. If we then made our conductor into a coil, so we have 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7 turns in this coil, then we can get the same effect. And the more turns we have in the coil, the bigger that induced current will be because of the bigger induced PD. The stronger the magnetic field, the bigger the induced PD will be, and so the bigger the induced current in this case. And if we make the magnet or the coil move faster, then we will get a bigger induced current. So it's all about the rate of change of the field through the coil, the rate of the cutting of field lines. So by having more turns in the coil, then you're getting more cutting per second. By having more field lines per square centimeter around the magnet, you're getting more cutting per second. By moving the magnet or the coil faster, you're getting more cutting per second. And all of these things, which lead to more field lines being cut or a greater rate of change of the field through the coil, these all produce a larger induced PD, and if we have a complete circuit, a larger induced current, as we have here. So then we can develop that into a generator. Here we have an AC generator. We have a coil of wire turning between the poles of a magnet, and we have our slip rings, which will carry our current out of our coil. And you can see we have a complete circuit here, so we will get a current. Now it's important that we can see and analyze the different positions of the coil and the induced PD that is produced. So if we look here, this is the value of the induced PD at this point, and it's gone past the horizontal. I didn't manage to stop it quite on the vertical. I didn't quite manage to stop it on the vertical. So it's a little bit below the zero here. When it's at the vertical, rather than cutting through field lines, this side and this side of the coil are just moving along field lines. And so there is no cutting, and so there is no induced PD, so there is no induced current. At the horizontal position, we're very nearly horizontal, and we're very nearly at the maximum value here. And as it goes round another half turn, you can see we're at a maximum positive value. So when the coil is moving through the horizontal position, then these sides, left and right, are cutting through field lines at a maximum rate. And so we have a maximum induced PD, and in this case, because we have a complete circuit, a maximum induced current. And in terms of using an oscilloscope or oscilloscope traces to establish the frequency of our signal, we look here and we are told that each 5 small squares is worth 0.005 seconds. And you can see going from here to here is 0.002. That is the time it takes to make one wave. That is the period. So the period is 0.002. Frequency is 1 over period, 50 Hertz.